The new chapter for the session is surface areas and volumes. What is a surface area and what is a volume? Now that we have discussed about area and perimeter in a solid closed figure, similarly we have the concept of surface area and volume, which mainly comes in the three-dimensional zone. So let's see in brief about surface areas and volumes of different solid figures. For example, if I have a different sheet of papers, say for example I have this paper which is rectangular, we know that this sheet of paper, when just understood, is understood as a rectangle with length and breadth. But what if I start adding another papers, like I had the set of papers joined together? So when the set of papers are joined together, then it seems to form a solid figure. So this kind of a solid figure, which is formed by each sheet of paper combined together to form a bundle of papers, is what makes us enter into the concept of surface areas and volumes. Similarly, if I take the example of this is a rectangular plank. This is length and this is breadth, but this is the length and this is the width, and also we see that it has slight thickness on the rim. So if we take into consideration even the three-dimensional thickness along with the length and width, such a concept makes us introduce or enter into the zone of surface area and volume. For a solid object, we also take into account the thickness, and this makes us understand why surface area and volume come into existence. So let's recap with area. As we have seen that area is this total region occupied by the closed figure. So this is the area of this face, but this being a solid object has areas in all the different directions. It has area here and here and here and here and here and here. So totally there are 6 different faces for this shape, which is called a cuboid in mathematics. So when it comes to a cuboid, let's draw a cuboid and just understand the concept. Here is the cuboid, assumed to be seen from this angle. Now there are totally 6 faces: face 1, face 2, face 3, 4, 5 and 6 down. So each of the faces have their own area, assumed to be a rectangle. So surface area is the area of each face of the solid figure. So we understand the surface area is defined as the area occupied by each face of the solid figure. So the surface area is defined as the area occupied by each face of the solid figure. So in this case, there are 6 faces which occupy 6 different areas. So when you add up all the 6 different areas together, then the total area is called the surface area of that object. In this case, it's a cuboid. What is the volume? So in general sense, as I see this object to occupy some space, like for example, this object occupies some space. So any object in universe which occupies space is called the volume. It is the capacity, and hence let's define volume in terms of the capacity of this box is to occupy this much of space, and hence its volume is what it occupies in the space. So, in general terms, the volume is defined as the space occupied by the solid figure, or sometimes we also call the volume as capacity. So the volume is also called the capacity in some other means of understanding the volume. So here the volume is defined as the space occupied by the solid figure, and the surface area is defined as the area occupied by each face of the solid figure. So each face area when added up gives me surface area, and the space which the object occupies is defined to be the volume of the solid figure. Is how we understand the surface area and volumes of a three-dimensional object. Now that we have discussed about surface area and volume of a solid figure is understood through the different faces as taken into consideration. Now let's see how we can find the surface area of a cuboid. This session is about surface area of a cuboid. Cuboid surface area. So how do we find the surface area of the cuboid? Let's see in brief. Imagine I take a cuboid which is in the shape of a box. Here is the cuboid, and here I have said the length of the cuboid is this, and the width of the cuboid is this, and the height of the cuboid is this. If the length, width and the height are given to be L, B and H respectively, then the surface area of the cuboid is nothing but the area of each of the 6 faces 1, 2, 3, 4, 5 and 6. So top, bottom and all the round faces make the surface area. So for such cuboid which has all the faces covered, we have surface area of the cuboid is 2 times of LB plus BH plus LH unit square. That's how we define the surface area of the cuboid. So the surface area of the cuboid, which covers all the 6 faces with length, width and height, is given by 2 times LB plus BH plus LH, where L is length, B is width and H is height. Surface area of a cuboid given by the formula. Now that we have discussed about surface area of a cuboid, let's see how we can apply to a real life problem. How to find the surface area of a cuboid whose dimensions are given using the formula. So this session is about applications of surface area of a cuboid. Applications of a cuboid. Say for example, the question says, find the surface area of the following cuboid. Then we have a cuboid which is like this, and here I have to find the complete surface area of this cuboid. So let's see how we can find the surface area. The dimensions out here are given to be 14 centimeter, 10 centimeter, and 4 centimeter. So let's see how we can use the surface area formula to find this. Clearly, the dimensions 14, 10, and 4 are nothing but the length, width, and height which we identify in the diagram. So for this cuboid, I identify that my length is 14 centimeter, my width B is 10 centimeter, and my height H is 4 centimeters. So LBH, length, width, and height are given out here. So using LBH, we have surface area of cuboid, which is given by the formula 2 times LB plus BH plus LH. So LB is 14 times 10, LB plus BH plus LH is what we get when we substitute L equals 14, B equals 10, and H equals 4, which on simplification gives 140 56. And this comes out to be 180 and 236. 472 is what we get. Therefore, area of the given cuboid is nothing but 472 centimeters square. centimeters square is the area of the given box or the given cuboid with length 14 centimeters, width 10 centimeter, and height 4 centimeter. Its area would be 472 centimeters square. Is how we apply the formula into the application based problem. Now that we have discussed about surface area of a cuboid, let's see how we can understand the lateral surface area of a cuboid with its real life model. Today's session is about lateral surface area of a cuboid. lateral surface area of a cuboid. So here is a cuboid with length, width and height. Now as we have seen that there are 6 faces, 1, 2, 3, 4, 5 and 6, the top and bottom. So if you add each of the 6 faces, we get the total surface area or the surface area of this entire cuboid. But if we just exempt the top and the bottom faces and we go laterally along the side, straight line along the side, then such an area is called lateral surface area. So the laterally surface area does not include the areas on the top and the bottom. It includes only the surface area on the sides. So face 1 plus face 2 plus face 3 plus face 4 make the lateral surface area. This and this does not come into account. So we understand that lateral surface area is the surface area of the cuboid which does not include the top and bottom. It includes laterally the side faces. So let's see in this session how to find the lateral surface area of a cuboid. Imagine I take a cuboid . Now here, this is the length, this is the width and this is the height. Now as I include only the 4 faces but not the top and bottom, this is not included and the bottom part is also not included. Only the face 1, face 2, face 3 and face 4 are included. Let's see how we can find lateral surface area of the cuboid. So here the definition says lateral surface area denoted by LSA is the area, is the surface area of the cuboid which does not, which includes all the faces which includes surface area of all the faces except the top and bottom faces is how I understand the lateral surface area. The area of the cuboid which includes all the faces except the top and bottom. Therefore, using that definition of the lateral surface area, therefore lateral surface area of a cuboid is given by LH and LH there and BH plus BH. Therefore, I have only 2 times of LH plus BH. I do not include the top and bottom which is LB, so it has only LH plus BH. Is how we understand the lateral surface area of a cuboid. 2 times LH plus BH. The top and the bottom faces are exempted in lateral surface area. Now that we have discussed about lateral surface area of a cuboid, let's apply in a problem. So let's see the applications of lateral surface area, how to find the lateral surface area of a given cuboid. Applications of lateral surface area. This is for a cuboid. So let's see how we can find the lateral surface area of a cuboid as the applications. Here is a rectangular cuboidal box. And this is 10 meters, and this is 8 meters, and this is 5 meters. So let's see how the lateral surface area, that is, which covers only this region and this region, but not the top and bottom, the other two sides. So the question here is, find the lateral surface area for the given cuboid. So let's see how we can do it. As clearly we have the dimensions, my L is 10 meters, my B is 8 meters, and my height is 5 meters. So I have my L, B and H, which I'm going to use in finding the lateral surface area. So in this case, lateral surface area of the given cuboid is given by the formula 2 times LH plus BH is what we have seen. So let's use this formula to find the lateral surface area. LH plus BH. So this comes out to be LH plus BH, and then 2 times 90, which is 180. Therefore, the area of the lateral surface area of the given cuboid is 180. Therefore, lateral surface area of the given cuboid is 180 meters squared. Is how we understand the lateral surface area, which can be found using the dimensions of the cuboid. In this case, the answer is 180 meters square. Applications of lateral surface area into the real life models. Now let's discuss about a cube. What is a cube and how do we derive from a cuboid? We have discussed the various properties in a cuboid, the total surface area and the lateral surface area. Now comes how we can take a cube as a special case of a cuboid. Today's session is about cube as this 3-dimensional solid figure. We all have come across the Rubik's cube, the one through which we solve the game. A Rubik's cube is a perfect cube because it has all its sides equal. So what is the special case? So we say that a cuboid whose all its sides are equal, such a cuboid is called a special name called a cube. So if I have all the sides being equal, then this is a cube because it has all its sides equal. This is an example of a cube because, say, this side is A, this side is A, and this side is A. Its length, its width, and its height are all equal in length. So we can define a cube as seen here with the dotted region . A cube is a special cuboid in which all its sides are equal in length. If you take the example of this, the length of this is not equal to length of this, or the length of this is not equal to length of this, or the length of this is not equal to length of this. So this cannot be a cube because a cube has a special case, is a special cuboid in which all its sides are equal in length. This length must be equal to this length, must be equal to this length. All its lengths must be equal. Only then we call the given cuboid to be a cube. A Rubik's cube is one of the example. We all know what a Rubik's cube is. So such a solid figure is given by the name cube. Cube is a special cuboid in which all its sides are equal in length. Now let's see what is the surface area of this cube to be followed with. Let's see now the surface area of the cube. So let's take a cube, as we have defined a cube to be a cuboid in which all its faces are equal. So here is the cube. And for this cube, each face are equal. So this are equal. Now for this cube of side A, we can find this total surface area or the surface area using the formula. Total surface area, or simply the surface area of a cube of side A is given by surface area of cube equals 6a square unit square. That's how we understand surface area of a cube as 6a square unit square. If I have a cube of side A, I can find the surface area by using the formula 6 times a square. Now that we have discussed about a cube and also about finding the surface area of a cube using the formula 6a square, let's see one of an example problem as the applications of surface area of a cube. This is about surface area. Now here I have a question which says, find the surface area of the following cube. So here I have a cube. And I need to find the surface area of this cube in which the side is given to be 5 centimeters. So surface area of the cube. So how do we find surface area of this cube? We have the formula directly, where first I identify that my A is 5 centimeters. So using A equals 5 centimeters, surface area of the given cube is 6a square, formula 6 times a square, which is 5 square, and 5 5 is 25, 25 6, which is 150. Therefore, surface area of a cube of side 5 centimeters is given to be 150 centimeters square. Is how we understand the surface area of a cube of side 5 centimeters is 150 centimeter square. Applications of surface area of a cube to an example problem. Now that we have discussed about total surface area of a cube, now comes the question on lateral surface area of a cube. As we have seen the definition of lateral surface to be the area of each of the faces which are on the side, excluding the top and bottom faces. Let's apply the same concept of the cuboid into the cube. Lateral surface area. So what is a lateral surface area of a cube? So let's take the diagram. Here is the cube. So let's see the area of this cube with side A, the lateral surface area of this cube with side A. Clearly we see that there are 4 faces excluding the top and bottom face, which makes the lateral surface area. So each of the faces is a square, therefore as we take the dotted region, there are 4 squares of side A which make the lateral surface area. So totally there are 4 squares which make the lateral surface area, and each of the square has the area A square. So 4 times of A square would be the lateral surface area. That's how we understand the lateral surface area of a cube. Therefore, lateral surface area of a cube of side A units is 4 times of area of each square, which is 4a square. Is how we get, because area of square is a square. Therefore, LSA of a cube is 4a square (4a square unit square), lateral surface area of a cube. Now that we have discussed about lateral surface area of a cube, let's try to apply in a problem. So applications of lateral surface area of a cube. So if I have a cube So here is a cube of side 7 meters, and my question is, find the lateral surface area of a cube of side 7 meters. So here is a cube of side 7 meters with all sides being equal. Now we need to find the lateral surface area. Now 7 meters is the A which I identified. So my side A is 7 meters and lateral surface area of a cube is given by lateral surface area of a cube is 4 times of A square, is what we have seen as the formula. 1, 2, 3, 4. 4 faces or the 4 squares which are taken into consideration. So let's see how we can add up. Now that we know the value of A is 7, I just substitute the value of A, which is this 7 sevens 49 meter square is what we get. So here the lateral surface area of this cube is 196 meter square. Therefore LSA of a given cube of side 7 meters is 196 meter square. This is what we get. The lateral surface area of this cube of side 7 meters is 196 meter square. Is how we conclude the applications of lateral surface area for solving the problems. This session is about cylinders. Now that we have discussed about surface areas and volumes, let's now enter into understanding what is a cylinder. As we have seen this real life model, I see that this CD stand clearly has various different CDs lined out on the rod. Now if I take one CD out from this, it looks like a circle. So I see this CD stand to be a set of all circles built up so that it forms a 3-dimensional shape. So let's understand a cylinder through the concept of the CDs. So a circle as in this model, when I take and I put another circle or a 1 rupee coin or a CD, as we have seen in this model, one over the other, we see that the different types of CDs as built forms a sort of a shape which looks like this. And this kind of a shape as formed by these CDs is nothing but a cylinder. So in mathematics, the set of infinite circles built on each other to form a cylinder is how we understand through the mathematical means. Now let's try to make it more brief about a cylinder. As we have seen, the different sets of circles but provided if I take two different CDs, I see that the two CDs are equal in size. The two CDs do not have different sizes, but the two circles are assumed to be of the same size. The rule for constructing a perfect cylinder is that all the set of infinite circles must have same size. This is how we understand the important means of constructing a cylinder. So as we come through the model, I see that all the all the circles which form the cylinder have the same size, and therefore it constructs a straight figure which is called a cylinder. Different set of circles of same size, to be noted down, form something like a three-dimensional object which is called a cylinder. So cylinder built from different set of circles constructed on each other, of course of the same size. This session is about understanding what a right circular cylinder is. Now that we have understood the cylinder to be constructed from set of circles, let's now try to understand the most important part of cylinder, which is called right circular cylinder in mathematics. This session is about right circular cylinder. What is a right circular cylinder? What is the difference between a cylinder and the specific cylinder given by the name right circular cylinder? So let's see this in brief. So as I see right circular cylinder, I have three different things which I understand: the one which is right, the one which is circular, and the one which is, of course, a cylinder. Circular and cylinder. So we differentiate a right circular cylinder into three classifications. One is this, this, and this. Let's understand each of this to understand the whole concept of right circular cylinder. As we see, right in mathematics means the one which is at right angle or 90 degrees is how we understand a cylinder. A cylinder which is exactly straight as 90 degrees is called a right circular cylinder. And of course, the cylinder must be circular. It cannot have a different shape other than each of the circles being constructed to form a cylinder. And circular at every stage. And equal in size is how we understand circular. And of course, it must be the shape of a cylinder, as we have seen in the previous model of the shape of a cylinder. So this is how it looks. It must be cylindrical in shape, as this we see as a cylindrical shape. Therefore, a right circular cylinder is a three-dimensional solid which is in the cylindrical shape and which has circles which are equal in size at every stage I take a CD here or here, at any stage of, they are equal in size. So circular at every stage and equal in size. Right, that is, it must be exactly 90 degrees to the ground. If the cylinder is cross, then we say it is not a right circular cylinder. The angle between the ground and the height at which the CDs rise must be 90 degrees. Right angle or 90 degrees is how we see a perfect cylinder. Is how I have the base which must be exactly from the ground at 90 degrees. Cylinder which is right circular has three important classifications. Right circular cylinder. Now that we have identified the definition of a right circular cylinder, let's see some of the objects which are right circular and which are not right circular. For example, I take a cylinder which is crossed. It is crossed out here, and then this kind of a cylinder cannot be right circular because the angle between the ground and the height at which the cylinder rises is not 90 degrees. That is, if I take this to be a ground, then this angle is theta, and here this angle is not equal to 90 degrees. Is how mathematically we identify a right circular cylinder. The angle between the ground and the height at which the cylinder rises must be 90 for the cylinder to be right circular cylinder. Theta is not 90 degrees. Therefore, the given cylinder is not a right circular cylinder. Since theta is not 90 degrees, therefore the given cylinder is not a right circular cylinder. Is how we understand. Let's take one more example to understand the classification between right circular and a non-right circular cylinder. For example, I take a shape which looks like a cylinder, but actually this solid is formed by constructing a different object which is in the shape of this. So each of a shape which is not a circle is constructed. If the shape, something which is like this, is used to construct just like an egg shape, so this is an egg shape which is constructed, then this cannot be a cylinder, right circular cylinder, because we demand for circular concept in right circular cylinder. So if this is egg shape, then this is not a right circular cylinder. Though it is 90 degrees from the ground, it cannot be right circular cylinder because it has to be a circles which are constructed to form a cylinder. The reason being, each of the constructed objects are egg-shaped. Is how we understand the right circular cylinder demanding for three different rules: this, this, and this. Now let's see one more solid object to understand right circular cylinder concept more stronger. Suppose I have a circular cylinder which bulges out here, like this. This seems to look like a cylinder, but this is not right circular, though it is 90 degrees from the ground and though I see this 90 degrees from the ground and I see this being a circle, still I say this is not right circular cylinder, because each of the circles as constructed in the cylinder are not of same size. So here it is very important to note that this kind of a cylinder cannot be right circular cylinder. This is not a right circular cylinder, as each of the circles as constructed to form a cylinder are not of same size. This is the main reason why this cylinder does not become a right circular cylinder. This is not a right circular cylinder, as each of the circles as constructed to form a cylinder are not of same size. They must be of same size. This is a perfect right circular cylinder because each of the CD of the same size is constructed to form a cylinder. Circle of same size makes a solid right circular cylinder. So now that we have discussed about a cylinder and a special case of a right circular cylinder, it is very important to note that unless otherwise stated, a cylinder is assumed to be a right circular cylinder. So in the syllabus, when we refer to the notation and terminology of understanding the cylinder, we understand that unless otherwise stated, a cylinder as mentioned in the topic refers to. So we indirectly refer to any problem related to the word cylinder is assumed to be right circular cylinder unless otherwise stated with something else. Refers to right circular cylinder is how we understand the notation and terminology in cylinder concept. Cylinder assumed to be right circular cylinder unless otherwise stated. Now that we have discussed about cylinder and its special case as a right circular cylinder, now let's see how a cylinder is constructed from a rectangle. This is quite interesting because if I have this rectangle out here on the plain whiteboard, how do I construct a cylinder from this rectangle as taken? So imagine this sheet of paper which is rectangular length and width of certain dimensions. If I roll this exactly, if I just roll out here, it forms a cylinder. We assume that this paper which is rolled forms a cylinder. Out here and down out here, it's open. So a cylinder formed through a rectangular sheet of paper is how we're going to understand. So this session is about understanding the construction of a cylinder from a rectangular sheet of paper. Cylinder from a rectangle, from a rectangular sheet. As we have seen, a rectangular sheet of paper, when rolled, forms a cylinder. It is very important to note that A cylinder which is formed from a rectangular sheet of paper is understood to be with what could be the length of the cylinder when compared to the rectangle. If the rectangle has the dimensions length and breadth, what could be the length of the cylinder is the biggest question. So here, when I take the sheet of paper like this, I have my height, which is nothing but the breadth. The breadth of the rectangle will be the height of the cylinder, because as clearly seen, we have this is length and this is breadth. So when I roll this cylinder, it is nothing but the height remains constant, doesn't change. That is, the breadth of the rectangle when rolled forms a cylinder of height with the same dimension as b. So the breadth of the rectangle will be the breadth or the height of the cylinder. So first thing we note is the breadth of the rectangular sheet is the height of the cylinder formed. As can be clearly seen here, the breadth of the rectangle is the height of the cylinder as formed. And the length of the rectangle, let's see what happens to the length of the rectangle. As we just take this and roll, this length of the rectangle forms to become the circumference of the circle. So here, the second point which I identify is that the length of the rectangular sheet, the length of the rectangular sheet is the circumference of the cylinder, that is the circular region formed. So the length of the rectangular sheet is the circumference, as can be seen here. This is the circumference forms with the length of the rectangle. So breadth becomes the height of the cylinder and the length becomes the circumference of the cylinder. So let's see how they are related. But the same sheet of paper, which is a rectangle, now becomes a cylinder. The same rectangular sheet now becomes a cylinder, is the cylinder, curved and with a circle. Now that we have discussed about a cylinder which is derived from a rectangular sheet of paper, now let's see what could be the surface area of a cylinder. The topic says surface areas and volumes, and hence, now that we have discussed about cylinder, let's see what is the surface area of a cylinder. So in this case, I see that a rectangular sheet with, let's see, the curved surface area of a cylinder. Let's come back to the rectangular sheet of paper when rolled forms a cylinder. Therefore, the same area as occupied by the sheet of paper will be the same area as occupied by the curved region of the cylinder. Is how we understand the same sheet of paper occupying the same surface area when it forms a cylinder. So therefore, here we identify that surface area of a rectangle, of a rectangular sheet of paper is equal to the same curved surface area of a cylinder. Curved surface area of a cylinder formed from it. So this cylinder is formed from it. So surface area of a rectangular sheet of paper is nothing but curved surface area of a cylinder. So when we want to find curved surface area of a cylinder, we connect that with area of rectangle. So here, curved surface area, which I denote by CSA, of a cylinder is nothing but area of rectangle, that is length into breadth. But my length, which forms the circumference as seen in the previous case, this gives me the circumference 2 pi r and this gives me the height h. So length becomes 2 pi r and the breadth becomes height. Therefore, CSA of a cylinder is 2 pi r h unit square. Is how we understand the curved surface area of a cylinder. If this is a cylinder, the curved surface area is only the curved part but not including the top and bottom. So curved surface area of a cylinder is 2 pi r h unit square. Pi is 3.14, r is the radius and h is the height. So r is the radius of the circle and h is the height of the cylinder. Is how we understand curved surface area of a cylinder, 2 pi r h. Now that we have discussed about curved surface area, there are other possibilities. What if I take a cylinder which is closed both on the top and the bottom lid? What if I have a cylinder which has a lid which is closed? So let's take the different cases of a closed cylinder. So this session is about finding the total surface area of a closed cylinder. So imagine I take a cylinder not here, and the radius of the cylinder say is r and the height is h. Now here the difference is that this cylinder is closed both at the top and bottom. So this is a closed cylinder. This is a cylinder which is closed both at the top and bottom. So here it is closed and even down the cylinder is closed. So a cylinder which is closed on the top and bottom. Let's see what could be the surface area of this kind of a cylinder. So here we have total surface area of the cylinder is 2 pi r h, because it is nothing but the curved surface area, which is the curved part, plus the top and the bottom. Like for example, I take this, the total surface area is the curved surface area plus the top surface and the bottom surface. So we take into inclusion all the three regions, the curved part plus area of circle or top circle and area of bottom circle. So curved surface, area of top circle and area of bottom circle. So I get this to be 2 pi r h plus pi r square plus pi r squared. So here this can be simplified. Pi r squared plus pi r squared is 2 pi r squared, which can be further simplified to take 2 pi r common, or h plus r. Interchanging r and h, I get 2 pi r into r plus h. Therefore, total surface area denoted by TSA of a cylinder is 2 pi r into r plus h unit square. That's how we understand the total surface area of a cylinder. On the top and bottom included is 2 pi r into r plus h unit square, where r is the radius and h is the height of the cylinder. Now that we have discussed about a cylinder and its curved surface area and the total surface area, now comes the next three-dimensional solid object called a cone. We all have come across a shape when we were wondering what could be the shape called in mathematical sense. Imagine we went to some ice cream parlor and we had a cone ice cream. So here we bring into concept of a cone ice cream, which very much defines a cone. So the cream out on the top, but as we see this, we clearly see this shape has its specific definition in mathematics. The cone, what we're talking about in cone ice cream, is nothing but which defines a cone in mathematical sense. A cone which looks like this without the cream would look in this manner, and such a shape is called a cone. This shape is called a cone. So what is a cone? What are its different properties? As clearly we see that each of the circles, just like in the previous problem, we had a cylinder taken as a real life model. Each of the discs, which was of the same shape, have been constructed to form a different shape called a cylinder. Now next we will investigate on what happens if I start reducing the shape of the CD as I go down. The first CD which is on the top, then the next CD if I put is a little smaller in size, then we get a shape which is quite different from a cylinder. Cylinder has all CDs of the same size, but a cone has all the CDs which are decreasing in size. So here I take a CD, then I take a smaller CD, the next smaller, the next. I get a kind of a shape which is called a cone. So circular regions which are placed in decreasing order until they reach to the 0 point is how we define a cone. A cone is a solid object obtained by set of decreasing circles until the size of each circle until the size of the circles reduce to 0 is how we define a cone in the mathematical sense. A cone is a solid object obtained by set of decreasing circles until the size of the circles reduce to the point which is the 0. So here at this point we call this as point 0. Through this point 0, we get a cone which is in the shape of a V-shaped object. A cone derived from an ice cream cone is understood in the mathematical sense through this definition. Set of circles diminishing to the point 0. Now that we have discussed about construction of a cone and understanding of how a cone is constructed using the circles, now let's enter into understanding a right circular cone. So what is a right circular cone? A cone which is exactly 90 degrees and circular in the bottom. So a cone here which is exactly 90 degrees with the base and this being a circle are the two important points which make a right circular cone. So a cone whose base is a circle and if the base is perpendicular to the height of the cone, then we say such a cone is a right circular cone. So let's take the definition of right circular cone. So here the definition says cone whose base is a circle and which is 90 degrees and whose height is 90 degrees to the base is called a right circular cone. Is called a right circular cone is how we understand a right circular cone. The base is a circle and the height is perpendicular to the radius. It's a right circular cone. This is not a right circular cone because its base, when connected with the height, is not 90 degrees. The angle made by the height with that of the base is not 90 degrees. So this is not a right circular cone. And this is a right circular cone. Now that we have understood a right circular cone, let's try to understand the curved surface area. What is the curved surface area of a cone or a right circular cone? So this session is about curved surface area of a cone. So let's see the curved surface area of a cone. Here is the cone. And here is the radius and here is the height. So we have a relation which says because it's a right circular cylinder, this is 90 degrees and I have here the slant height L. So I have three different dimensions. L, which is called the slant height of the cone. And R, which is called radius of the cone. And H, which is called height of the cone. Slant height, radius and height are the three important things which define the curved surface area. So the curved surface area is the curved region of the cone, which is exactly the curved part but not the base. So curved surface area denoted by CSA of a cone is pi r. R is radius, L is slant height, pi is 3.14 approximately. Curved surface area of a cone or a right circular cone is pi r L unit square. Now that we have discussed about curved surface area of a cone, now let's see what happens if I add the base, which is a circle, to the curved surface area. Obviously, we get the total surface area. The curved region and the base add up to form a total surface area of the cone. This session is about total surface area of a cone. So let's take a cone. We have the radius and the height and the slant height. So let's see what is the total surface area of this cone. So clearly the total surface area of a cone is nothing but the curved surface plus the circle, is curved surface area plus area of circle, which is obviously the bottom. So here we have already derived for curved surface area in the previous session of the cone to be pi r L, and area of circle we all know is pi r square, with r is the radius and the base is the circle. So taking common, I can remodify this as pi r into r plus L or L plus r is how I get total surface area of a cone. Therefore, total surface area of a cone with radius r and slant height L is given by pi r into r plus L. Total surface area of a cone is pi r into r plus L unit square. Now that we have discussed about a cone or a right circular cone with its curved surface area and total surface area, now let's find what important relation between the radius, height and slant height of a cone. This session is about the relation between r, h and L. Radius, height and slant height of cone. Radius, height and slant height of cone. So here I have the radius, here I have the height, and here I have the slant height. And of course, this is a right circular cylinder, so this is 90 degrees. Now clearly I see that this OAB forms a right angled triangle. As can be seen here, B forms a right angled triangle OAB. Now in this case, OA is radius, this is height, and this is slant height. We clearly see that this is a right angled triangle, so the first thing which strikes my mind is Pythagoras theorem, of course. So in triangle or in right angled triangle OAB, if I use Pythagoras theorem, AB squared, that is hypotenuse squared, is OA squared plus OB squared by Pythagoras theorem. That implies AB, which is L, makes out to L squared, which is OA, which is R squared, plus OB, which is H squared. So here, the relation between L, R and H is L is root R squared plus H squared, or L squared is R squared plus H squared. The radius, height and slant height of the cone are related with L squared equals R squared plus H squared. R, L and H of the cone connected with this equals this. Now that we have discussed about cylinder and a cone, now the next solid object which we are going to define in the topic is sphere. This session is about sphere as a specific solid object in 3D. What is a sphere? How does it look like? Imagine I take a football or a basketball. So assuming this to be a basketball, the kind of a shape which it looks circular in all directions is called a sphere. So a basketball is the shape of a sphere. But how do we define a sphere in general sense of understanding through mathematics? As we have seen different shapes, like a basketball which looks like a sphere, a cricket ball which looks like a sphere, a football which looks even like a sphere, a football which looks like a sphere, a cricket ball which looks like a sphere, a basketball which looks like a sphere, the sun which also looks like a sphere when seen, is all what we have different objects which look like a sphere. But what is the sphere? How do we understand through mathematics? Is what we are going to see in the next session. Now let's define sphere in more mathematical means. Sphere, with its definition, a sphere is the set of points in space. Importantly to note, in space, a sphere is the set of points in space which are equidistant from a fixed point. That's how we understand a sphere. So set of points which are taken in the space are equidistant from a fixed point. That is, when I take the fixed point in the center and spread all the points which are equidistant, then I get a three-dimensional object which is a sphere. and the distance from center to this is called radius, and this fixed point is called center of sphere. So here the fixed point is called center, and the distance from fixed point to any point on the set of points is called radius. This is how we understand a sphere whose radius and fixed point define a sphere. Set of points in the plane which are equidistant from a fixed point is called a sphere. Now that we have defined a circle, so a sphere in mode of three-dimensional object, let's see what could be the curved surface area of a sphere. This session is about curved surface area of a sphere, or we can simply call this as surface area of a sphere because every corner of the sphere is curved. So this can also be referred to as surface area of a sphere. So a sphere which has the radius r, so this sphere which has the radius r is given by surface area of sphere is given by 4 pi r squared. That's how we understand the surface area of sphere is 4 pi r squared. R is radius of the sphere. Now that we have discussed about sphere, let's try to see what would happen if I cut the sphere exactly at the center. So imagine I have a sphere which is cut exactly at the center. So I cut the sphere exactly at the center in this region, then I get two separate regions. Which are separated like this. So we have two different shells which are obtained when I cut the sphere exactly in the center. Each of the shell is called hemisphere. This session is about discussion of hemisphere. So each of them are called hemispheres. So let's define the surface area of a hemisphere. Now this is the curved region which defines for the surface area. So the curved surface area and if this circle is added up to this dotted region, then that becomes total surface area. So curved surface area is the dotted region and the total surface area is both the dotted region and the curved region. So this is how we differentiate between the curved surface area as denoted by the dotted region is the only curved part of the hemisphere, and total surface area which includes the bottom and also the top of the hemisphere is how we are going to discuss the formulae for curved surface area and total surface area of a hemisphere in the following session. Now let's see the curved surface area of a hemisphere. I have a hemisphere in which curved surface area of hemisphere as denoted by the dotted region as given here is given by 2 pi r squared, where r is the radius of the sphere. R is the radius of the sphere. Curved surface area of hemisphere is 2 pi r squared. Let's see the total surface area. Now next comes the total surface area. Total surface area of hemisphere as given by the two regions. One is the dotted, one is this. Is curved surface area, which is the dotted, plus the total, this area of circle, which is given by this region. So this represents CSA and this represents a circle. So area of circle. Now curved surface area is already found to be 2 pi r squared. And area of circle, we all know, is pi r squared. Therefore, 2 pi r squared plus pi r squared is 3 pi r squared. This is nothing but the total surface area of the hemisphere. CSA 2 pi r squared, TSA 3 pi r squared for a hemisphere. In mathematics, volume is defined to be the capacity or the space which it occupies in the three-dimensional space. Suppose I take this marker pen, which looks like the shape of a cylinder. This seems to be occupying certain space in this area, and this space occupied is nothing but we define in mathematics as capacity or the volume of this object in the space. So let's see some volume formulae for the three-dimensional solid figures which I have discussed in the past sessions. To start with, cuboid. This session is about volume of a cuboid. What is the volume of a cuboid? Let's see the formula derived for a cuboid and its volume. I have a cuboid which looks the shape of a rectangular box. Now this is a rectangular box which is in the shape of a cuboid. We have its length, its width, and its height. A cuboid has three main important dimensions. One is the length, one is the width, and one is the height. And how do we find the volume of this cuboid? Is all based on the length, breadth, and height of the dimensions. So for this cuboid, volume of a cuboid is given by the formula LBH unit cube. So if I have the length, the width, and the height of the cuboid, I just multiply all the three dimensions, which gives me the volume of a cuboid. That's how I understand volume of a cuboid. For example, I have a cuboid with the dimensions 2, 3, and the width is 2 and the height is 4. Then having the length as 3, width as 2, and the height is 4, I have the volume of cuboid, which is given by the formula length into width into height, that is 3 times 2 times 4. Because my length is 3, width is 2 and height is 4, I get this to be 3 2 6, 6 4 24. And if the dimensions are centimeters, then all the dimensions give me the volume as centimeter cube. Is how I understand finding the volume of cuboid when its dimensions are given. Volume of a cuboid with the length L and the width B and the height H is given by the formula LBH unit cube. Now that we have discussed about a cuboid and its volume, now comes the discussion of volume of a cube. We all know that a cube is a special case of a cuboid where its length, width and height are of same dimensions. Therefore, let's see how the volume of a cube is derived using the concept of volume of a cuboid. I have my cube. Say its side is A, then all its dimensions are same. That means I understand that if this is a cube, then its length is A, width is A, and my height also is A. Therefore, my volume of a cube is LBH, A times A times A. So I get the formula which says volume of a cube as a special case of a cuboid is LBH, but my L is A, width is A, and height is A, which gives me A cube. Therefore, volume of a cube is A cube unit cube. That's how we get. So if you know the side of a cube, just cube it and we get the volume of the entire cube. Is how we understand the volume of a cube, understood through the formula of cuboid. Volume of a cube is A cube unit cube. So for example, if I take a cube of side 2 dimensions or 2 meters, then volume of this cube whose dimension is 2 meters is given by 2 cube, because we have the formula A cube with A equal to 2. I have this 2 cube which is 2 times 2 times 2 and 8 meter cube. Is how we understand the volume of the cube given its dimension. Is given by the formula A cube unit cube, where A is the side of the cube. Now that we have discussed about a cuboid and a cube with their respective volume formulae, now comes the question of what could be the volume of a cylinder. This is the shape of a cylinder and I would like to know what is its volume. So let's see in brief in this session about volume of a cylinder. We all know that a cylinder is in the shape like this, and we know that for this cylinder we have the radius which is denoted by R and the height which is denoted by H. So here is the radius of the cylinder and here is the height of the cylinder. So let's see what is the volume of cylinder based on radius and height. So here the radius and the height of the cylinder define the volume. volume of cylinder is given by pi r square h unit cube is what we have as the formula. Volume of cylinder is pi r square h unit cube, where r is the radius and h is the height of the cylinder. So let's see how we can solve some example problems using this formula. For example, I have a cylinder whose radius is 3 centimeters and height is 4 centimeters. So I would like to just find for this formula. So in this case, volume of given cylinder is given by the formula as we've taken here, pi r square h. So pi and r square, we know that the radius here is 3 centimeters and the height h is 4 centimeters when compared with r and h of the given problem. So using this r and h into the formula, I get r square into h. And this, on further simplification, gives 3 3s 9, 9 4s 36 pi centimeter cube. So volume of the given cylinder with radius 3 centimeter and height 4 centimeters is 36 pi centimeter cube, using strictly the formula out here. Therefore, volume of cylinder is given by the formula pi r square h unit cube. Now that we have discussed about a cylinder and its volume, now comes the next question. What could be the volume of a cone? In similar manner, in this session, let's see how we can derive the formula for volume of a cone. We all know that a cone has its own shape. So taking the shape of a cone, which looks somewhat like this, and then fixing from here, from the center, this distance is called radius and this distance is called height. So in a cone, we define this to be radius and this to be height. And using the dimensions of radius and height, of course, we have a slant height denoted by L. So by using the dimensions of R, H and L, we can define the volume of a cone, which is given by the formula volume of a cone is 1 by 3 pi r square h unit cube. Is how I get the formula. Volume of a cone is given by 1/3 pi r square h. Note, it's a very important note I make here, that volume of cone is 1/3 of the volume of cylinder from which it is derived. This is very important to understand because we understand a cone being generated from a cylinder. So volume of a cone is always 1/3 of the volume of the cylinder, which you already discussed in the previous session as pi r square h. So 1/3 of volume of cylinder from which it is derived. What do we mean by from which it is derived? For example, I take a cylinder Imagine I cut the cylinder exactly from center. So that I get something like this. So we assume that if a cylinder is cut into three parts, part 1, part 2 and part 3, this clearly is said to be a cone which is generated from this cylinder, and hence a cone generated from a cylinder is 1/3 part of the entire cylinder, and hence volume of a cone is 1/3 of the volume of cylinder from which it is derived. Cut the cone, you get 3 equal parts, and hence this volume of a cone would be exactly 1/3 of the entire cylinder, covering part 1, part 2 and part 3. Is how we understand a very important geometrical concept connecting cylinder and a cone, given by this relation. Volume of a cone is 1/3 pi r square h, where r is the radius and h is the height of the cone. Now that we have discussed about a cylinder and a cone, now the last geometrical structure, solid figure, which we're going to discuss now is about a sphere. What would be the volume of a sphere is what is today's session. So let's see what could be the volume of a sphere. Imagine I take a sphere which is this, and say the radius of the sphere is, say, r, capital R. If the radius of the sphere is r, then the whole of the volume is based on the radius. So here we have a formula which says volume of a sphere is given by 4/3 pi r cube unit cube. Volume of a sphere is 4/3 pi r cube. Is how we understand, with r being the radius. So with this, it's clearly understood that if the volume of a sphere is 4/3 pi r cube, then volume of a hemisphere is half of the volume of the sphere, that is 2/3 pi r cube unit cube, because exactly a hemisphere is nothing but half of the sphere. So we have this to be, this is the radius and this is the hemisphere, which has 2/3 pi r cube unit cube. Volume of a sphere is 4/3 pi r cube. Volume of a hemisphere, which is exactly half of the sphere, is 2/3 pi r cube unit cube, where r is the radius of the sphere. Let's see some example problem to understand the concept more stronger. For example, I have a sphere whose radius is say 3 centimeters. Let's see what could be, whose radius is say 3 meters. Then volume of the given sphere whose radius is given to be 3 meters is clearly given by the formula 4/3 pi r cube. So 4/3 pi r cube, which is substituted with the value of the radius r. This gives me 3 squared 9 9 fours 36 pi meter cube, is how we understand The volume of the sphere with radius 3 meters is 36 pi meter cube. Answer in terms of pi. Using the formula 4 by 3 by r cube. Volume of sphere and volume of hemisphere.